Welcome to week 1. This week is all about an algorithm that you use every day in your life. Autocorrect. You use autocorrect in your phone, on your computer, in text documents, when sending a message, almost everywhere you write text. This is why it's very interesting. It's that it's not a very complicated technology, and this week we will show you how to build it. This week you'll be calculating probabilities to find the most likely correction of a typo. You'll be processing data, doing some string manipulation, finding different possible edits to correct the typo, and finally finding the minimum edit distance to correct a certain word. By finding the minimum edit distance, you will be learning about dynamic programming, which is a very common interview topic question. Jonas will show you how to use dynamic programming to find the minimum edit distance.
Okay, great. Follow me. Welcome. This week, I will go over autocorrect. It is how your misspelled words are corrected automatically to the right ones. You know it's already from your email client on your phone. Let me show you how it works.
So let's go over this week's learning objectives. You'll learn about autocorrect conceptually. You've most likely used it in your phone or word processor. But what is autocorrect exactly? It can mean slightly different things depending on the context. You'll learn about the nuances this week. You will practice building a model to perform autocorrect. You will learn each step in autocorrect and key concepts to prepare you for the coding assignment. When performing autocorrect, you'll want to be able to quantify how far apart or different two strings are, and ask how many letters you can change to go from one string to another. To do this, you will learn to measure minimum edit distance. You will implement a really interesting algorithmic approach for solving the minimum edit distance called dynamic programming. At the end of the lecture, you'll demonstrate your new skills and put all these techniques to work in this week's assignment.
Exciting content. I'm looking forward to tell you everything about how you will be building your autocorrect. One very important concept is that the autocorrect you will be building uses dynamic programming. This comes up again and again in technical interviews. But first, let's get started with an overview of autocorrect in the next video. I will give you a brief overview of autocorrect and how it works. You will learn to identify misspelled words, what is an edit distance, and how to calculate probabilities of the correct word. So let's get started with a simple definition.
So what is autocorrect? Autocorrect is an application that changes misspelled words into the correct ones. You probably know it very well already. You have it on your phone, tablet, and on your computer inside your document editors and email applications. For example, it takes a sentence like this one, "Happy birthday, de friend," and corrects the misspelled word de to a word that you probably intended to write, which in this context would be dear, correctly spelled D-E-A-R. But what if you typed dear instead of dear? Here you see the word is spelled correctly, but its context is incorrect. Well, unless your friend happens to be an actual deer, you will not test for this kind of contextual error this week, as it's a more sophisticated problem. You'll get to learn about that another time. Instead, this week you'll only look for words that have been misspelled and make corrections to these. This involves a simple yet powerful model, as you will see. Let me show you an overview of how autocorrect works. There are 4 key steps. First, identify an incorrect word. Misspelling is one way to do this. Second, find strings 1, 2, 3, or any n edit distances away. Don't worry, you will learn about minimum edit distance shortly. For now, what's important to know is that if a string is 1 edit distance away from the string that you typed, it's more similar to your string compared to a string that is 2 edit distances away. Third, filter these strings for real words that are spelled correctly. And fourth, calculate word probabilities, which tell you how likely each word is to appear in this context, and choose the most likely candidate to be the replacement. So now you have a better intuition for what is autocorrect and how it works. That's good. Next, you'll take a closer look at the details for implementing each step so that you can begin to build the autocorrect model.
Now you know how autocorrect works. In the coding exercise of this week, you will implement it and see for yourself that it works really well. Next, I'll show you how to speed up edit distance computation. In the previous video, I briefly mentioned the 4 steps required to implement autocorrect. Now, you're going to take a deep dive into these steps.
You already know the 4 steps inside the autocorrect model, so it's time to look at each step in detail. You'll be implementing each of these steps in this week's assignments. Step 1. Identify a misspelled word. When the string de is encountered, how do you know it's a misspelled word? Well, if it's spelled correctly, you'll find it in a dictionary. If not, then it's probably a misspelled word. If a word is not given in a dictionary, flag it for correction. Recall that you are not searching for contextual errors, just spelling errors. There are much more sophisticated techniques for identifying words that are probably incorrect by looking at the words surrounding them, some of which you'll visit later in the course. But for now, quickly identifying a word as incorrect by its apparent misspelling is a simple yet powerful model that works well. So words like deer will pass through this filter just fine, as it is spelled correctly, regardless of how the context may seem. Step 2. Find strings that are 1, 2, 3, or any number n edit distance away. When saying n edit distance, I'm referring to an edit distance of n, such as edit distance of 1, edit distance of 2, and so on. An edit is a type of operation performed on a string to change it into another string, and edit distance counts the number of these operations, so that the n edit distance tells you how many operations away one string is from another. Now consider an insert operation, for example. This is a type of edit that adds a letter to a string in any position. For example, starting with the word to, insert a P at the end and you get top, or insert W in the middle and you get to. A delete operation removes a letter. For example, start with the word hat, delete T from the end and you get ha, or delete H from the front and you get at, or delete A from the middle and you get the string HT. A switch edit swaps to adjacent letters. For example, the string ETA. Switch T and A and you get EAT. Or switch E and T and get T. Notice that you are switching 2 letters that are next to each other. So this does not include switching 2 letters that are not next to each other, such as switching the E and the A to make 8. A replace edit changes 1 letter to another. For example, the word jaw. Change W to R and you get jar, or change J to P and you get paw. So using the 4 edits, insert, delete, switch, and replace, you can modify any string. And by combining these edits, you can find a list of all possible strings that are n edits away. For autocorrect, n is usually 1 to 3 edits. You will implement each of these edits in this week's programming exercise, and combine edits to get a list of 2 edit distances from the original input string. Now step 3, filter candidates. Notice how many of the strings that are generated do not look like actual words. To filter these strings and keep ones that are real words, you only want to consider real and correctly spelled words from your candidate list. So again, compare it to a known dictionary or vocabulary, just like in step 1. This time, if the string does not appear in the dictionary, remove it from the list of candidates. When you're left with a list of actual words only, then that is good progress. That's the first 3 steps of building the autocorrect model. In the next lesson, you'll see the 4th and final step.
You learned about 3 of the 4 steps required to implement autocorrect for the first week. The first step was identifying the misspelled word. Then, finding the strings that are n edit distances away. Then, filtering the candidates that are actual words. Now the last step is calculating the probabilities, which you will learn about in the next video. Good to see you again. As promised in the previous video, I will now show you how to calculate the probabilities of each possible correct word.
Now that you have a list of actual words, you can move on to step 4. Calculate word probabilities. The final step is to calculate word probabilities and find the most likely word from the candidates. For example, the word and is more common than the word ant in any given body of text, also called a corpus. This is how autocorrect knows which word to substitute for the incorrect one. To understand this better, look at this example sentence. I am happy because I am learning. To calculate the probability of a word in this sentence, you need to first calculate the word frequencies. In addition, you want to count the total number of words in the body of text, or corpus. Normally, a corpus would be much larger. Imagine every issue of a certain magazine ever published, or all of the Harry Potter books. To keep this example as simple as possible, the corpus here is defined as this one sentence. For example, the word I appears twice. The word am appears twice also, and so on for the rest of the words. The total number of words in this corpus is 7. The probability of any word within the corpus is the number of times the word appears divided by the total number of words. For example, the word am appears twice and the size of the corpus is 7. For autocorrect, you find the word candidate with the highest probability and choose that word as the replacement. And that's it. In summary, to implement autocorrect, you did the following. You entered a word to correct, for example, the misspelled word de, D-E-A-H. Then you followed the 4 steps inside the autocorrect model to get its replacement. You identified de as being misspelled by checking it against known words. Then, you made a list of all the strings that are n edits away. You filtered this list of strings to include only the ones that are actual words in a given dictionary. And then you calculated the word probabilities for each of these words. You selected the word with the highest probability as the autocorrect replacement, and that was it. That's a lot to cover, but breaking it down step by step gives you a good intuition for how to implement autocorrect. This is something that will come in very handy for the assignment, so well done. Also, you now understand edit and edit distance, and how they can be used to measure similarity between words. Next, get ready to apply these concepts to building a metric very common in NLP for measuring similarity between words, strings, and many more.
You have seen the 4 steps required to implement autocorrect for this week's programming assignment. This is exciting. Now in the next video, we will look at how we can evaluate similarity between 2 strings. For example, a word with a typo and a word without. Minimum edit distance has a wide variety of applications. It allows you to implement spelling correction, document similarity, machine translation, DNA sequencing, and more. I will also show you the different types of edits.
You have already seen how to build autocorrect using edit distance, but consider a slightly different problem. What if you were given 2 words, strings, or even whole documents and you wanted to evaluate how similar they are? Minimum edit distance can be used to do this. Given 2 strings, the minimum edit distance is the lowest number of operations needed to transform one string into the other. It has many applications. In NLP, for example, it could be used in spelling correction, document similarity, and machine translation. It can also be found in computational biology and DNA sequencing. For calculating minimum edit distance, you will use 3 types of edit operations. All 3 operations that you already know: insert, delete, and replace. For example, to turn play into stay, what is the minimum number of edits required to make this happen? So to turn P into S, you replace P with an S. And to turn L into T, you replace L with a T. Both A and A are the same, so do nothing. And it's the same with Y and Y. So the total number of edits is 2. Until this point, you've considered all edit operations to cost the same, that is, a cost of 1. But now you'll consider a different cost for each type of operation. You will use these costs to calculate the edit distance, which now represents the total edit cost. This is what you are trying to minimize. It is simply the sum of costs for the edits that were made. Insert and delete will have a cost of 1, and replace has a cost of 2. This makes intuitive sense if you think of replacement as a delete followed by an insert. Calculate for this example. You have 2 replace edits at a cost of 2 each, for a total edit distance of 4. This is a relatively simple example, and it was possible to find the minimum edit distance just by looking at it. But imagine the number of operations between much longer strings and large corpora of text, or even DNA strings. You can try and solve these problems by brute force, adding one added distance at a time and enumerating for all possibilities until one string changes to the other. But this could take a very, very long time. In fact, by solving this way, the computational complexity increases exponentially as each string grows in length. A much faster way is by using a tabular approach. You'll implement this next.
The tabular approach I spoke about allows you to speed up the enumeration of all possible strings and edits. In doing so, you will also be learning about a new concept known as dynamic programming. We'll see about this in the next video. Welcome! In this video, I will teach you about dynamic programming. We will go through one example, but once you understand that, you'll be able to apply dynamic programming to anything.
So you start by laying out the problem like this, where you have the source word play here, down the left column, and then the target word to transform into stay, along the top row here, and an empty string placeholder represented by the hashtag symbol at the start of each string here. The reason for this will make more sense in the steps ahead. There are also some row and column indices here, just to make things a bit easier to follow along. Now the goal is to fill out this distance matrix D, such that the element D23, for example, refers to the minimum added distance from PL to STA, which is the first two letters of the word play to the first three letters of the target word stay. Or more generally, for any element in the matrix by using this formula for the element at row I and column J, being I equals 2 and J equals 3 in the example PL to STA. From the previous few slides, you know each D of ij will be the minimum added distance between the beginning of the source word to index I and the beginning of the target word to index j. So that for a source of length m and a target of length n, when you get to the bottom right corner, d of mn, you have the minimum added distance between the two strings. You will compute this from the shortest substring to the full string. That is, starting with the shortest string in the top left corner and working down then to the right. The intuition is that you can build upon each subproblem by combining solutions. For example, finding the minimum added distance between two letters is easy. Then you increase the problem size one letter at a time, building on what you already know. If this seems confusing at first, don't worry. It is, but it will start to make more sense as you work through the example. But first, before you get started, recall the cost for each edit. 1 for insert and delete, and 2 for replace. Okay, so the first step is to transform the source empty string into the target empty string. The added distance between the source empty string and the target empty string is 0. There's no formula here, it's just a special case. So far, so good? Okay, to change nothing to nothing, you do nothing. Good. Then you can move on to P, to empty string. And you can do this with a delete edit operation at a cost of 1. Then empty string to S, which you can do with an insert edit operation at a cost of 1. Now look at P to S. There is more than one possible way to make this transformation. Each possible sequence of edits is known as a path. Starting with P, you can insert S on the end to get PS. Then delete P from the beginning to get S. This has a cost of 1 insert and 1 delete. At this point, notice that you've already calculated the cost of inserting a letter S. It's found in this red box here on top, when you calculate how to get from empty string to S. So you actually just calculate the cost of deleting the P and add it onto the cost that you've stored in the red box above. This is 1 plus 1 equals 2. In the second possible path, starting with P, you can delete P to get hashtag, and then insert S to get S. Notice again that you've already calculated the cost of deleting P in this blue box in the left. The blue box is the cost of going from P to hashtag by deleting P. So you can calculate the cost of inserting P and add it to the cost that you've stored in the blue box on the left. This is 1 plus 1 equals 2. The third way is to replace P with S, so that you go from P to S in one step, at the cost of 2 for replacement. Visually, you can think of going from this green box and jumping directly into the orange box. The green box is the cost of not doing any edits, which is 0. A replacement has a cost of 2, so 0 plus 2 equals 2. Then, you take the minimum of all three of these paths, which is a 2 in this case. Then place that value in the cell which gives you the minimum edit distance from P to S. So working off what you've already filled out, you'll notice that to fill in a cell, you need to know the cell above, to the left and adjacent upper left, shown in red, blue, and green here. In doing so, you can benefit from some calculations already performed. Soon, I'll show you how to generalize this in a formula to fill out the rest of the matrix. But first, I will show you how to fill out the first column and the first row so that every cell remaining has its own red, blue, and green cells available as dependencies. This is what's coming up next.
In this video, you learned about the cost of each operation. Insert and deleting is 1, and then replacing is 2. You also saw how you can populate your table. In the next video, you will learn about a much faster way to populate your table. In this video, we are going to translate how to populate the table mentioned previously used to change from one word into another with some code. By the end of the video, you'll see the finished product.
Earlier, you used an intuitive approach to fill out the upper left corner of the minimum edit distance table. Now, I'll show you how to use a formulaic approach to fill out the rest. So you filled out some of the table already, and it looks like this. Now, to fill out the rest of the table, you must first fill out the remaining cells of the leftmost column and top row. In fact, you know that to transform play into an empty string, you can just delete each letter. So let's try that. You can fill out these cells, top to bottom, by following this formula. For each cell, look at the cell above and add the cost of an extra delete edit, which will be 1. This means that to make the string P into the empty string, do one delete operation. As shown in the previous example, to turn the string PL into the empty string, delete P and delete L, which are 2 delete operations, and so on. Now, at D40, you have the minimum edit distance for play to the empty string, which of course is just the cost of 4 deletes, 4. You can use the same idea in the first row by transforming the empty string to stay by inserting one letter at a time. You do that by following this slightly different formula. Working from the left to the right, look at the previous cell and add a further insert cost 1. Looks good so far. In the previous example, I showed you how to calculate this cell without formulas. But you can also find the solution by applying this big, scary looking formula. It builds upon the computations you've already made in just the same way as using the no formula method. Some of this might feel like it's repeating what you just learned, but it's valuable to see the formulas too, especially when getting ready for the end of week assignment. So the distance to this orange cell is going to be the minimum distance to reach it from any of the previous 3 cells. Interesting, right? It might seem a little bit abstract at first, but you can break it down into smaller parts. For example, if you come from the cell above, you will add a delete cost, just like you did in the first column. If you come from the cell to the left, you will add an insert cost, just like you did in the top row. And if you come from the cell to the upper left, you will do one of 2 things. Either add a replace cost if the 2 letters source I and targets J don't match, or add nothing if they do, because there is no edit to be done for letters that are already the same. So here for this cell, you have the minimum of 1 plus 1, which is 2. Another 1 plus 1, which is 2. Since these 2 letters don't match, you have 0 plus 2, which is also 2. Then you take the minimum of all 3 of these, which is a 2 in this case. Place that value in the cell. This is the minimum edit distance from P to S by using the formula and costs defined. You can then fill out the rest of the table the same way, with the MN entry in the bottom right corner being the minimum edit distance from play to stay, which is 4. Adding color coding or a heat map reveals some interesting patterns. Can you see what's happened from the middle square? That's right. Once you get from PL to ST, the suffix of both words is the same, AY. So there are no more edits needed. And that's why this 4 carries down the diagonal. Now you know how to build a minimum edit distance algorithm efficiently using a table. Well done. There are a few things worth noting about this style of implementation before you go. I'll show you those next.
Congratulations! Now you have seen some code that you will be using in the programming assignment. In the next video, I will show you some more tricks that will help you with the programming assignment. See you soon! This video gives you a complete overview of minimum edit distance and shows you what to do if you want to reconstruct the path you took when doing the edits. Let's dive in.
A few quick notes on the minimum edit distance implementation you learned. Measuring the edit distance by using the 3 edits, insert, delete, and replace with costs 1, 1, and 2, respectively, is known as Levenshtein distance. That's what you've used here. You can look it up for more details if you like. There are also well-known alternatives that have different edit rules. Finding the minimum edit distance on its own doesn't always solve the whole problem. You sometimes need to know how you got there too. You do this by keeping a backtrace, which is simply a pointer in each cell letting you know where you came from to get there. So you know the path taken across the table from the top left corner to the bottom right corner. This tells you the edits taken and is particularly useful in problems dealing with string alignment. But that's a discussion for another time. Finally, this tabular method for computation instead of brute force is a technique known as dynamic programming. Intuitively, this just means that solving the smallest subproblem first and then reusing that result to solve the next biggest subproblem, saving that result, reusing it again, and so on. This is what you did here by solving each cell in order. It's a well-known technique in computer science and will appear again and again in the coming weeks of this course. And that's it. This was a long lesson, so well done. You should be proud of yourself. You took the problem of solving minimum edit distance and broke it down into parts. Then, used a tabular-based approach, step by step, for a very efficient implementation. Great work. Now try the programming assignment where you will code up this example, with an optional challenge to build a backtrace tool. What a journey! And you're just getting started here. The weeks ahead are loaded with more exciting stuff. But before you go, a quick recap. In the past few lessons, you learned a lot about some real-world applications of NLP that you're probably using every day. You learned about autocorrect, and what it is and how it works its magic. You went step by step through how to build a working autocorrect model using edit distance and word probabilities. You learned about the problem of string similarity and metric of minimum edit distance. And finally, you learned a really cool way to solve minimum edit distance using a tabular algorithmic technique known as dynamic programming. You now have the know-how to practice all these new skills in the Week 1 programming assignment. Have fun and good luck!
Congratulations on finishing the week. Minimum edit distance introduces your first application of dynamic programming. In the next week, you will learn about the Viterbi algorithm, which also makes use of dynamic programming. See you soon!
Good job in learning this week's materials. You now know how dynamic programming works, and you can see why it is a very powerful algorithm. Just like how you can use dynamic programming to find the minimum edit distance between two strings, you can also use it to find the shortest path from point A to point B to point C, like in Google Maps. These are some very powerful models that you learned. In this week's programming assignment, you will be implementing autocorrect, and by the end of the assignment, you will be able to feed in a typo to your model, and it will give you the most likely correction. Autocorrect these days uses a lot of techniques, but you will get a good baseline and understand how the concepts work. You will also learn about dynamic programming in the assignment. Next week, you'll tackle part of speech tagging. Good luck in the assignment.